In 2013, scientists attempted to recreate the evolution of the universe from shortly after the Big Bang until today. This simulation, which took 19 million CPU hours to produce, started with a predicted amount of matter, and dark energy that should have existed shortly after the Big Bang. The simulation was allowed to run to see if these parameters that were set at the beginning can produce the galaxies and the universe's structure we see today. What you are looking at here is limited to a 32 million light-year cube of the simulation. The expansion of the universe is considered, with simply gas density and temperature visible. This is the intergalactic medium. Even though space is a vacuum, there are still a few particles in every cubic centimeter of space. Blues are the coldest regions here, whites are the hottest. As gas particles are drawn together by their own gravity and that of dark matter, the gas clumps, and over the course of millions of years coalesces into galaxies, which increases the gas's temperature drastically. What you'll immediately notice is that there appear to be explosions coming from the densest clumps. But galaxies exploding? That can't be right, I surely would have heard of that before. But remember, this is the intergalactic gas temperature we are seeing. And each second passing in the video is a few million real-time years. Quasars, or extremely active black holes, are the brightest objects in the universe, emitting more electromagnetic radiation than entire galaxies combined. When a quasar lights up, its rapid increase in radiation blasts into space, ionizing the intergalactic gas as it expands out, heating it up to extreme temperatures. This is known as quasar mode, or active galactic nuclei feedback. Black holes don't remain as quasars for lengthy periods of time. Rather, quasars are the result of a large amount of mass falling into them, lighting them up and causing them to eject huge amounts of mass and energy. They'll remain as quasars as long as there is matter being fed into them. Although, you may wonder, how can a black hole emit anything? Don't they absorb it all? And the answer is yes. It is in fact the accretion disk around the quasar that is so energetic and luminous. A black hole's accretion disk is the result of matter passing by, being ripped apart and sucked into orbit. These supermassive black holes often have billions of solar masses. The gravity around them is immense. As the material in the accretion disk orbits and falls inwards, the friction from the material in the disk rubbing together creates energy so intense that a quasar can be thousands of times brighter than our Milky Way. In fact, a quasar's host galaxy is often too dim to detect next to the bright quasar, although techniques with the Hubble Space Telescope have allowed a few of these host galaxies to be seen too. Quasars could light up from collisions of galaxies, when suddenly an abundance of matter falls into the supermassive black hole, although this doesn't always happen. You'll also notice these jets coming from the quasar's poles. These extend well beyond the galactic disk and can be seen illuminating other galaxies and dust clouds like a spotlight. Quasars themselves are bright, but when these jets are pointed towards us, they are known as blazars. The jets are believed to be powered by the black hole's magnetic structure, and they can carry high energy plasma away from the black hole at almost the speed of light. The days of quasars and blazars are thought to be over. The closest quasar to us is 600 million light years away, and thus was going on 600 million years ago. However, you'll notice that the explosions in the simulation don't let up in this video as time passes. This comes from the last in the active galactic nuclei family of black holes, radio galaxies. Typical quasars and blazars are so bright that they light up in all frequencies of the electromagnetic spectrum uniformly. Radio galaxies originate from black holes that, unsurprisingly, are brighter in radio wavelengths. These explosions now come from radio galaxies, and this is known as radio mode feedback. The simulation stops at the present day. Now, while impressive, the simulation isn't perfect. For instance, it could only simulate 1 trillion particles compared to the countless number of particles in the equivalent section of space. Also, we don't have a perfect knowledge of the perimeters of the universe, and so there were certain mistakes evident in the model, like the overprediction of star formation. There are plans to try this again at some point, with an updated understanding. Being able to model how the universe evolved can give us a confirmation about how we believe it formed, and this is of great interest to scientists. Let's see what future results will bring. So, can galaxies explode? Not in the conventional sense, but if you are talking about exploding with electromagnetic radiation, then absolutely. In October 2022, a brilliant flash pierced the cosmos, brighter and more intense than anything human civilization had ever seen. And that's not an exaggeration. The strength of the blast blinded our gamma ray detectors the world over and unleashed more energy in a matter of seconds than our sun will emit over its entire 9 billion year lifespan. Over the 18 months that followed, it became the most widely studied gamma ray burst in history, creatively dubbed the Boat, for the brightest of all time. As researchers began to decipher its cause, their findings unraveled one mystery after another. Scientists have been cataloguing gamma ray bursts for decades, but this one was closer, brighter, and unexplainably devoid of some key signatures you'd expect to see. It also raises some far-reaching questions about our standard model, the possibility of a dark matter particle, and how heavy elements like gold are made. I'm Alex McColgan, and you're watching Astrum. Join me today as we dive into the mystery of the biggest and brightest gamma ray burst of all time. What caused such a colossal explosion? How is it different from other gamma ray bursts before it? And what can it teach us about our understanding of the universe and the particles that constitute it? Gamma ray bursts are brief, intense flashes of high-energy gamma radiation lasting from milliseconds to several minutes. The first of its kind was detected in 1967, when American satellites designed for detecting covert Soviet nuclear testing picked up an unusual pattern of electromagnetic energy. Since then, gamma ray bursts have been of tremendous interest to the cosmological community, as they allow scientists to study states of matter and physics that are not reproducible on Earth. Essentially, they provide researchers with a glimpse of how stars are formed and evolve across the whole timeline of the universe. There are two different kinds of gamma ray bursts. Short gamma ray bursts last less than 2 seconds and are attributed to either the collision of two neutron stars or the merger of a neutron star and a black hole. They can be followed by a kilonova, an emission of bright light resulting from the radioactive decay of chemical elements. This decay creates even heavier elements, an important feature of novae which we'll discuss more later. Anything lasting longer than 2 seconds is classed as a long gamma ray burst. These are thought to be caused by the explosive deaths of massive stars and their subsequent supernovae. The collapsed core may form either a neutron star or a black hole. These typically occur close to the edges of the observable universe because they are characteristic of low metallicity stars which formed when there were less heavy elements around. When we see one of these, we are witnessing events from billions of years ago. In the case of both long and short gamma ray bursts, the newly formed black hole blasts out jets in opposing directions, containing particles accelerated close to the speed of light. When these particles interact with surrounding matter, they emit the gamma rays we detect. So, what made the Boat so special? Let's start by analyzing some of its key characteristics. Firstly, the Boat lasted 10 whole minutes. and was detectable for 10 hours after the fact. It occurred in the Sagitta constellation, only 2 billion light years away, which is much closer than other gamma ray bursts we've detected until now. In fact, such a bright explosion so close to Earth is thought to be a 1 in 10,000 year event, meaning the last time one happened, humans had barely started farming. As is the case with other long gamma ray bursts, we know a collapsing and exploding star was behind it, but this is where things start to get fuzzy. A supernova alone isn't enough to explain the magnitude of the gamma rays emitted. The boat was a whopping 70 times stronger than any other gamma ray burst detected. Initially, the theory was that this must be the supernova of a ginormous star, the likes of which we rarely see. However, upon closer inspection of the afterglow, scientists found that the supernova behind the boat was shockingly ordinary. To get a clearer picture, astronomers pointed the James Webb Space Telescope in the boat's direction. Webb's near-infrared spectrograph revealed that the supernova behind the boat was actually pretty average. It wasn't nearly as bright as you'd expect given the gamma ray burst that accompanied it. So what could have caused such a flash? One idea is that we simply perceive the flash as bigger and brighter because of Earth's relative position to the blast. Imagine a flashlight shining in the dark, diffuse and soft. It lights the path 1 to 2 meters ahead of you. Now, imagine capturing all that light and focusing it into a singular laser beam. It wouldn't illuminate the path as widely, but it would reach hundreds of meters into the distance. And if Earth was in the direct path of that laser, it would register a super bright reading. That doesn't mean the laser released more energy than the flashlight, it just means the way it was concentrated and then detected resulted in a higher reading. The same concept can be applied to these gamma ray bursts. If a massive star is spinning super fast when it collapses, then the shape and structure of the near light speed jets it emits will be more narrow and focused, and therefore brighter. In fact, the jets seen from the boat are some of the narrowest we've ever seen. But not only were these particle jets brighter than expected, scientists also detected way more of them going faster than expected. They traveled with such fervor that after 2 billion years traversing the cosmos, they arrived here and momentarily disrupted the Earth's atmosphere. Sitting just 50 to 1,000 kilometers above the surface of our planet, Earth's ionosphere is rich in electrically charged particles. When the boat struck, it left a mark comparable to that of a major solar flare, pushing the ionosphere down into lower altitudes. If photons from an explosion 2 billion light years away can have this kind of effect on our planet, I don't really want to think about what happens if something like that in our neighborhood explodes. The large high-altitude air shower observatory in Daocheng County, China, managed to capture data on tens of thousands of photons over the course of the initial blast and into the afterglow. This is a quantity unlike anything seen before in gamma ray astronomy. In fact, it's so far out of pocket that some astrophysicists think that they might be pointing towards something missing from our models. According to our current understanding, it's very unlikely these super high energy photons are traveling for 2 billion years. Cosmic microwave background radiation, interactions with intergalactic dust, or redshifting caused by the expansion of the universe are all factors that can interfere with a photon's trajectory. One hypothesis put forward is that photons convert themselves into a hypothetical particle called an axion, and then convert back into gamma rays upon reaching our galaxy's magnetic field. Axions are thought to be an ultralight particle responsible for dark matter. Their existence is currently purely hypothetical. We have no evidence for them, and even if we did, they would lie outside the standard model of particle physics. We don't have time to delve into detail in today's video, but let me know if you'd enjoy a separate video on this in the comments. Okay, so far we've established that BOAT was caused by a massive star collapsing and turning into a black hole, which incidentally is known as a collapsar. Aside from generating a long gamma ray burst, collapsars are also known for generating something else. Gold. Wait, how is gold connected to gamma rays? Good question. To understand that, let's take a minute to discuss how elements are made. The core of a star is a super high pressure environment, some 200 billion times higher than the atmospheric pressure on Earth. In these conditions, nuclear fusion reactions create heavier elements out of lighter ones. For example, one helium atom comes from fusing 4 hydrogen atoms together. Elements 2 through 26 on the periodic table, that's helium to iron, are made this way, a process known as stellar nucleosynthesis. However, once you get to iron, it isn't energetically favorable to continue making bigger and bigger elements this way. So how do we account for the rest of the periodic table? Where do these heavier elements like gold come from? At the moment, we know 2 different ways these elements are formed. The first was recently confirmed by the James Webb Space Telescope. When 2 ultra-dense neutron stars collide, they emit an immense amount of neutron particles. Surrounding material captures these neutrons, making their atoms temporarily unstable. In order to stabilize, the neutrons undergo radioactive decay into protons, creating new, heavier elements. This process is known as rapid neutron capture, or R-process nucleosynthesis. Some calculations suggest one neutron star collision can produce up to 3 Earth masses worth of heavy elements. However, this explanation alone isn't sufficient to account for all the heavy elements in the universe. Neutron star collisions are rare and take a long time to happen, in the order of billions of years. On top of that, observations of very old stars show that heavy elements were already present in parts of the universe well before most binary neutron stars would have had a chance to collide. So how do you explain that? There must be another source of heavy elements in the cosmos. Which brings us back to our boat. There's another theory that collapsars like the boat could be another source of R-process nucleosynthesis. In their dying stages, massive stars like the one that caused the boat are surrounded by layers of exploding gas. These explosions leave disks of matter swirling around the resulting infant black hole. As the black hole begins devouring the surrounding material, it can only ingest so much at a time. What it cannot manage is swept away in a neutron-dense wind. Here, the same R-process nucleosynthesis occurs, forming heavier elements like gold, silver, and platinum. This seems promising, but unfortunately, even factoring in these kinds of supernovae isn't enough to account for the abundance of gold in the universe. To make matters worse, analysis of the boat spectrum didn't show any traces of heavy elements, raising questions about the validity of this collapsar gold-making theory. Some scientists suggest the boat's host galaxy might have something to do with the lack of heavy elements in the explosion. Upon modeling the host galaxy spectrum, researchers discovered it has the lowest metallicity of all previous host galaxies where gamma-ray bursts were detected. In other words, maybe the environment didn't have the right building blocks to make heavier elements. How do we know how much gold should be out there in the first place? How do scientists predict something like the relative abundance of elements in the universe? There are 2 main methods of calculating this: the spectroscopy of stellar photospheres and meteorite analysis. By analyzing the absorption lines in the spectra of stars, astronomers can determine the relative abundances of elements in the photosphere of those stars. The composition of meteorites, remnants of an early solar system, are analyzed in parallel to determine the relative abundances of elements. Meteorites are especially useful for measuring the abundances of volatile elements like hydrogen, helium, and noble gases that are unrepresented in stellar photospheres. The results of both of these methods are usually congruent, indicating we're probably doing something right. But this is physics, so of course nothing is so cut and dry. One famous exception to this rule is lithium. According to the standard Big Bang nucleosynthesis theory, the early universe should have produced about 3 times more lithium-7 than is currently observed. The plot thickens when we consider its isotope, lithium-6, where we observe 1,000 times more than our predictions can account for. This discrepancy is known as the lithium problem and remains unsolved, presenting a significant challenge to the standard cosmological model. It highlights the importance of understanding the processes that shape the relative abundances of elements in the universe, and suggests that our current understanding of nucleosynthesis might be incomplete. Just because boat didn't yield gold as expected doesn't mean we should discard these kinds of extreme gamma-ray bursts as places where heavy elements could be made. Observations of nearby stars have provided strong evidence for an early R process that enriched the universe with heavy elements. But the boat findings cannot be ignored, as they suggest there may be alternative, currently unknown processes responsible for this elemental enrichment of our cosmos. The results may call into question our entire model of understanding regarding collapsed stars and their role in creating heavy elements. This discovery is much bigger than just the boat or gamma rays. It's about the literal building blocks of our universe as we know it. Where do our different atoms come from? And why do they exist in the proportions they do? How much of our model is accurate and how much is missing? What role does dark matter play in all of this? We need more time and research before we know for sure, but the boat is a great example of how new findings keep our understanding of physics ever evolving, just like the universe itself. Imagine standing on a quiet hill, watching the sky burst into a symphony of colors as the sun peaks above the horizon. It's a daily spectacle that many of us take for granted. The warm hues of orange, red, and pink splashing across the sky. Yet, this beautiful sunrise is only the final chapter in the light's long journey. If we trace the path of these photons from their endpoint in the retina at the back of your eye, through the Earth's atmosphere, across the 150 million kilometer void separating our planet from its host star, and finally through the varied and tumultuous layers of that star, we discover the source of the warmth on your face and the colors painted across the sky. The sun's core, a nuclear engine that has been raging for 4.5 billion years. Born in a cosmic nursery from the remnants of ancient stars, the glowing sphere of searing plasma that dominates our sky is the product of complex forces that have played out over millennia. So let's take a journey back in time, tracing the origins of the sun, exploring its intricate layers, and mapping the elements that make up its very structure. I'm McColgan, and you're watching Astrum. Join me as we dive into the depths of our sun and learn what secrets lie behind the blinding curtain of light and time. To understand how the sun formed, we must go back to before our solar system even existed, about 4.6 billion years ago. At that time, in a relatively quiet region of the Milky Way galaxy, a massive cloud of gas and dust, known as a giant molecular cloud, drifted silently through space. This was no ordinary cloud. It was immense, possibly spanning hundreds of light years across, with a mass equivalent to millions of suns. Within this cloud lay the scattered remnants of ancient stars that had long since exhausted their nuclear fuel and exploded as supernovae, casting their enriched contents into the cosmos. This stellar debris included a mix of elements such as hydrogen and helium, the building blocks of stars, along with heavier elements like carbon, oxygen, nitrogen, and iron. The presence of these elements made this molecular cloud fertile ground for forming new stars and planetary systems. However, such a massive cloud requires a trigger to initiate the cascading collapse that results in stellar birth. Scientists believe that this trigger could have been a shockwave from a nearby supernova explosion that compressed parts of the cloud, causing it to fragment and collapse into regions of higher density. This collapse marked the beginning of the pre-solar nebula, the dense region within the molecular cloud that would eventually give birth to our solar system. Some scientists have even proposed a name for this hypothetical exploding star, Coatlicue. Named after the Aztec goddess of earth and fertility, Coatlicue symbolizes the death and rebirth cycle, where in this case, the death of one star can seed the formation of new ones. As the gravitational collapse of the giant molecular cloud progressed, it did not result in a single massive object, but rather fragmented into multiple dense clumps. This fragmentation occurs due to a phenomenon known as Jeans instability, named after the British physicist Sir James Jeans. The Jeans length is a critical distance within a cloud at which the forces of gravity are balanced with the natural internal gas pressure that keeps the cloud propped up. When a defined section of the cloud exceeds the Jeans length, it will collapse in on itself. Different regions within the molecular cloud exceed this Jeans length at different times due to variations in density and temperature. As these regions become gravitationally unstable, they collapse independently to form multiple protostellar cores as opposed to one single massive body. The protostellar core was the earliest phase in our Sun's life that was recognizably star-like, crunching itself into a tighter and tighter sphere by the ever-clenching fist of its own gravity. The core is surrounded by infalling gas and dust. As more material accumulates, the core becomes denser and hotter, setting the stage for the next phase of star formation, the protostar. Once a protostellar core becomes sufficiently dense and hot, it evolves into a protostar. The central region has heated up to the point that it begins to emit light and heat from the energy released by gravitational contraction. But its core has yet to reach the temperatures required to ignite nuclear fusion in the core. As the protostar continues to accumulate material and grow in mass, the pressure and temperature in its core increase dramatically. Our Sun developed through this embryonic state of contraction and heating for millions of years, before eventually building up its core temperature to about 10 million degrees Celsius, at which point hydrogen nuclei began to fuse into helium. And with that, the Sun was born. At this stage, the innate angular momentum of the surrounding material that shrouds the infant star generates rotation. A cloud of this size will always have some slight rotation, nothing in the universe is still, and conservation of angular momentum dictates that the cloud must spin faster and faster as it crunches down into tighter space, similar to how a spinning figure skater speeds up as they tuck in their arms. Around the equator of rotation, some of the material is moving fast enough to stay in orbit, but higher up and lower down, the momentum is insufficient to resist the protostar's ravenous pull and falls helplessly into its jaws. And so, the cloud flattens out into a disk, a protoplanetary disk. This disk is a cosmic lottery. As it cools and coalesces, planets, moons, asteroids, and comets will be relentlessly created and destroyed. Some material will be robbed of its momentum and tumble into the Sun, while neighboring matter will go on to become part of the many bodies that make up our solar system today. With its new ability to fuse hydrogen atoms into helium, the Sun could finally generate energy to push back against the forces of gravity that sought to squeeze it further. The energy streaming out of the fusion reactions created an outward radiation pressure that balanced the inward gravitational pull of the gas, allowing the young star to achieve a stable state known as hydrostatic equilibrium. In this state, the star no longer contracts under its own gravity, and it enters a stable phase of its life known as the main sequence. This balancing act between internal pressure pushing outward and gravity crushing in is the axis that defines every stage of the Sun and all stars' lives. We saw it during the initial collapse, and here as it settles into a stable main sequence star, and it will be the pendulum that eventually swings towards its dramatic death. For now, let's unpick the process of nuclear fusion and how it's capable of keeping an object as massive as the Sun stable and steady for billions of years. To understand how nuclear fusion occurs in the Sun, we need to examine extreme conditions present within its core. Today, temperatures reach around 15 million degrees Celsius and pressures more than 250 billion times that of the Earth's atmosphere. In this blazing cauldron, hydrogen atoms are stripped of their electrons, forming a plasma composed of free protons and electrons. Under such intense conditions, these protons, normally repelled by their shared positive electric charges, are forced into extremely close proximity. The force that usually keeps them apart is the Coulomb force, an electrostatic repulsion between positively charged particles. It's exactly the same force that resists as you try to push the same ends of a bar magnet together. Overcoming this force is the primary challenge for nuclear fusion to occur. Despite the extreme kinetic energy of protons in the Sun's core, most collisions are still not energetic enough to overcome the Coulomb barrier. Under normal conditions, protons need immense energy to get close enough for the strong nuclear force to bind them together. This barrier is so significant that physicists around the early 1920s, using a classical understanding of how particles interact with each other, determined that fusion should not occur at the temperatures and pressures found in the Sun's core. To solve the puzzle, we needed a scientific model that has come to explain many of the seemingly impossible phenomena we observe in the universe: quantum mechanics. The quantum mechanics revolution of the 1920s introduced the concept of particles behaving both as particles and as waves. One of these phenomena is quantum tunneling, where particles have a certain probability of tunneling through a barrier even when they lack the classical energy needed to overcome it. In the Sun's core, quantum tunneling allows a small fraction of protons to effectively bypass the Coulomb barrier without having to climb over it in the classical sense. Even though these protons do not have enough kinetic energy to overcome the electrostatic repulsion directly, quantum mechanics gives them a chance to appear on the other side of the barrier. To visualize this process, consider a diagram of the Coulomb barrier. In the diagram, you will see a high energy barrier representing the repulsive electrostatic force between two protons at varying distances. The energy needed to climb over this barrier is represented as a peak. The calculations of a classical physicist would require the Sun to have temperatures high in the billions of degrees Celsius, thousands and thousands of times higher than the Sun's core, to hurdle this barrier. But quantum mechanics allows for the probability wave of a proton to tunnel through this barrier, appearing on the other side without ever going over the peak. This tunneling effect is what enables fusion to occur in stars like the Sun, despite the seemingly insurmountable Coulomb barrier. Once a proton has tunneled through the Coulomb barrier, it gets close enough to another proton for the strong nuclear force to take over. The strong nuclear force, which is far more powerful than the Coulomb force, operates only at very short ranges, on the order of femtometers, where 1 femtometer is equal to 10 to the power minus 15 meters, roughly the size of a single proton. The strong nuclear force binds the protons together, but this is only the first step in a series of nuclear events known as the proton-proton chain. The proton-proton chain reaction is the dominant fusion pathway in the Sun and other stars of similar size, accounting for roughly 99% of the Sun's energy production. It starts with 2 free-roaming protons combining to form deuterium, a heavy isotope of hydrogen, along with the emission of a positron and a neutrino. This step is rare but essential, as it allows the fusion process to continue. The deuterium then rapidly fuses with another proton to form helium-3, releasing a high-energy photon, a gamma ray. In the final step, 2 helium-3 nuclei collide and fuse to form helium-4, releasing 2 protons and a significant amount of energy in the form of radiation. While the proton-proton chain is the dominant fusion process in the Sun, there is another pathway at play particularly in stars hotter and more massive than our Sun. This pathway is known as the CNO cycle, short for carbon, nitrogen, oxygen. In this cycle, carbon, nitrogen and oxygen nuclei act as catalysts to fuse protons into helium. The CNO cycle is more efficient at higher temperatures and only contributes a small percentage of our Sun's energy output. The energy produced in these fusion reactions comes from a small amount of mass being converted into energy, as described by Einstein's famous equation E equals mc squared. In the fusion process, the mass of the resulting helium-4 nucleus is slightly less than the combined mass of the original 4 protons. This missing mass is not lost, but rather converted into energy that radiates outward from the Sun. Every second, the Sun converts about 4.3 million tons of its mass into energy. That's right, the Sun is losing mass all the time. To put this into perspective, this is the equivalent of the mass of about 3 million cars being turned into pure energy every second. This is the energy that ultimately powers the Sun and provides the light and heat that reaches Earth. But before these photons pouring out of these reactions can reach the Earth and everything else in the solar system and beyond, they must first escape the 700,000 kilometers of chaotic solar interior that lies above them. To truly grasp the complexity of the Sun and its stratified layers, let's follow a single photon, a particle of light, from its creation within a proton-proton reaction all the way to the surface. This journey is anything but straightforward. In fact, it will take thousands, if not hundreds of thousands of years for this photon to complete its journey, passing through several distinct layers of the Sun, each with their own unique properties and behaviors. As we've already found out, our photon's journey starts in the core, a region that spans about 25% of the Sun's radius, but holds nearly half of its total mass. And, as we've also heard, the core is incredibly dense, at around 160 grams per cubic centimeter. It's over 20 times denser than iron. To put that into perspective, if your phone was made of material that dense, it would weigh as much as a heavy-duty sledgehammer. For our photon, this means that the environment is so tightly packed with particles, it cannot travel far before being absorbed by a neighboring particle. Of course, not long later, that particle will pack the photon's bags and send it out into the melee of the core for another particle to catch and release in some other random direction. It's a bit like trying to navigate through a dense crowd, where every few steps you bump into someone and have to change direction. This constant interaction of absorption and re-emission is what gives the core its chaotic nature, resulting in a journey for a photon that is more of a random walk than a direct path outward. This random movement of photons is reminiscent of Brownian motion, where particles suspended in a fluid move erratically due to collisions with smaller, fast-moving molecules. And there is no preference for the direction that a photon could fly back out of a particle that had just absorbed it. In theory, a photon could make it all the way to the surface of the Sun before random chance directs it back towards the core. To add to the complexity, as photons are continuously absorbed and re-emitted, the energy gradually decreases from gamma rays to X-rays and eventually to visible light as they move towards the Sun's outer layers. Understanding the processes occurring within the Sun's core has been a challenging endeavor for astronomers. The core is completely obscured by the outer layers of the Sun, meaning we cannot directly observe it through any form of light. Instead, scientists have developed ingenious methods to infer the dynamics of the roaring inferno below. One of the key techniques is the study of helioseismology, the observation of waves rippling across the Sun's surface. Just like seismologists study earthquakes to understand Earth's interior, helioseismologists measure the vibrations of the Sun's surface caused by sound waves that travel through its interior. These sound waves are influenced by the temperature, density, and composition of the sun's layers, allowing scientists to construct models of what is happening deep within. Solar neutrinos, elusive subatomic particles that I've talked about in a previous video, are also released during the fusion reactions in the sun's core. Neutrinos interact so weakly with matter that they can travel straight out of the sun in just 2 seconds, hardly aware of the tangle their photon counterparts are caught up in. For decades, solar neutrino detectors on Earth measured fewer neutrinos than predicted by theoretical models, leading to what was known as the solar neutrino problem. It wasn't until scientists discovered that neutrinos change their properties, or flavors, on their journey to Earth that the mystery was resolved, confirming both our understanding of particle physics and the nuclear processes in the sun's core. Next, the photon enters the radiative zone, which extends from the edge of the core to about 70% of the sun's radius. Here, temperatures gradually drop from 15 million degrees to around 2 million degrees Celsius. The density of matter also drops, going from around the density of gold in the zone's depths to less than water near the top. The dominant energy transportation method is still this frenetic process of photons skittering through the layer, carrying their energy on average towards the surface. And as the density of the plasma continues to decrease as we move outward, our photon has slightly more wiggle room, capable of bigger leaps between interactions. But even here, outside of the core, the sun's material is still so opaque that even a few centimeters could block out as much light as hundreds of meters of water. We are able to envision such precise models of the sun's interior because of models like the Standard Solar Model, or SSM. It is a mathematical framework based on the principles of hydrostatic equilibrium, energy conservation, and radiative transfer. Essentially using our understanding of how materials and fluids behave here in our laboratories on Earth to infer the properties of a place out of our reach. The SSM models how energy is passed between particles in its complex equations, describing how photons are transported through the dense plasma. This allows us to calculate how transparent the solar material is to radiation at different temperatures and densities, and from there we can work out where the radiative zone ends and the next layer begins. This is one of my favorite things about mathematics. It allows us to explore environments that we can never visit, almost like how quantum tunneling allows protons to jump over the Coulomb barrier and produce the photons we are now following. As our photon approaches the upper boundary of the radiative zone, it enters the tachocline, a thin, transitional layer where the radiative zone meets the next layer, the convective zone. The tachocline is an environment of extreme contrast, where the relative uniformity of the radiative zone meets the boiling, bubbling convective zone. The strange conditions in this extremely thin layer likely plays a key role in the solar dynamo that generates the sun's magnetic field. The tachocline is thought to twist and amplify the magnetic field, shaping the sunspots and solar flares that define the star's surface. Zipping through the thin tachocline, our photon arrives at the convective zone, stretching out from about 70% of the sun's radius to just beneath the visible surface, the photosphere. The temperatures have dropped to below 2 million degrees Celsius. Now, the sun's plasma is no longer dense enough to effectively transfer energy by radiation. Instead, the plasma becomes unstable and begins to move in massive convection currents, much like boiling water in a pot. Hot plasma rises towards the surface in large cells called granules. These granules, with diameters of thousands of kilometers, surge upward under their power of buoyancy at speeds of hundreds of meters per second, like a beach ball that you force below the water, rushing to the surface as it squirms from under you. The force required to move this volume of matter against the sun's gravity is astonishing. Imagine the force of 10 billion hurricanes, and you'd be just starting to get close to the energy necessary. This convective process moves energy much more efficiently than the radiative zone, creating turbulent, rolling waves of plasma that churn vigorously. I have explained these convection cells and the beautiful hypnotic patterns they create on the sun's surface in a lot of detail in this previous video. This is a significant change in how energy is transported. While photons still interact with particles, the primary mechanism of energy transfer in the convective zone is no longer the random absorption and re-emission between particles, known as radiative diffusion, but rather the movement of hot plasma rising and cooler plasma sinking. This convection motion carries the energy outward more efficiently than in the radiative zone. Upon reaching the top of the convective zone, the photon is carried to the photosphere, the sun's visible surface. Temperatures have now cooled to about 5,500 degrees Celsius, and the plasma has thinned enough for photons to escape without being constantly reabsorbed. It is from this thin, roughly 500 kilometer deep layer that the light we see from the sun is emitted. Above them lies only the sun's corona, which is itself a fascinating environment, but only around a billionth of the density of the photosphere, and therefore not much of an obstacle to our photon. It is incredible that an object like the sun, that many refer to as a ball of gas, can have such a sharp boundary. But the photosphere is where our photon finally breaks free, traveling at the speed of light and beginning its journey across the vastness of space. Our neutrino friend that was created at the same time? It's long out of the Milky Way by now. Since settling into its stable main sequence phase, nuclear fusion has altered the strength of the sun's layers, gradually increasing its brightness over billions of years. This is because the fusion process inevitably leads to changes in the composition, density, and temperature of the sun's core, which in turn affects the overall behavior and the future of our star. As hydrogen fuses into helium, hydrogen gradually depletes in the core, and helium ash begins to build up. Unlike hydrogen, which readily undergoes fusion at the sun's current core temperatures, helium requires much higher temperatures to fuse. As the abundance of helium increases, the core becomes denser. Helium nuclei are more massive than hydrogen nuclei, and as more helium collects in the core, the overall density increases. At the same time, because helium is not fusing and creating energy, it does not contribute to the outward radiation pressure that counterbalances the sun's immense gravitational pull. The result is that gravity will begin to dominate, causing the core to contract further. To prevent collapse under its own gravity, the sun must increase its core temperature as helium builds up. The hotter core turns up the dial on hydrogen fusion because nuclear fusion rates are extremely sensitive to changes in temperature. This increase in fusion releases more energy, which results in a brighter star and temporarily restores the balance between gravity and radiation pressure. Through this process, the sun's energy output has increased by about 30% over its lifetime, and this trend will continue for billions of years as long as hydrogen fusion dominates in the core. In the radiative zone, the layers have grown hotter and more opaque. The rising temperature of the core means more energetic photons are produced, which are more prone to interacting with the surrounding plasma and pinballing around. As a result, this zone has become less efficient at radiating energy outward, trapping photons for longer before they can continue their escape. The convective zone has also expanded slightly over time due to the increased energy production. As the sun continues to burn through its hydrogen fuel over the next 5 billion years, its core will eventually be left overburdened with inert helium that can no longer sustain fusion under its own pressure. When this happens, the sun will evolve into a red giant, dramatically expanding and engulfing its inner planets, including Mercury and Venus and possibly the Earth. In this phase, the core will contract and heat up until it ignites in a helium flash, starting the fusion of helium into heavier elements like carbon and oxygen. yet again swinging the pendulum between the relentless gravitational hammering and the resisting forces of energy from the core. This process will create new layers and cause the Sun to swell even further before shedding its outer layers to form a ghostly remnant, a planetary nebula. The core that remains will cool and fade, becoming a white dwarf, a dense, Earth-sized ember of a once raging fire. This transformation from a stable star to a red giant and eventually a white dwarf is a remarkable and complex process with many fascinating details, which we will no doubt explore in a future video. But ending our journey from the depths of the Sun's ancient past to its modern interior, let's return to that quiet hill where we began, watching the colours of sunrise. I hope the next sunrise you see becomes that little bit more special. I hope the pink and orange photons, scattered for one final time on the molecules of Earth's atmosphere before streaming through your pupils, will make you think of the incredible voyage they have endured, beginning with the collapse of a colossal cosmic cloud into an element-building furnace, struggling for hundreds of thousands of years through a melting pot of plasma to gift you with this beautiful scene. I hope this exploration has deepened your appreciation for that daily miracle we often take for granted. And there's still so much more to uncover about our closest star, from the formations it will undergo to the profound impacts it will have on our solar system's future. Thank you for joining me on this journey through space and time. If you found this journey as enlightening as our host star, please give the video a like and fuse it with your own thoughts down in the comments below. Thanks for watching. Beneath its swirling clouds, Venus is a world of relentless heat, crushing pressure, and volcanic plains stretching for hundreds of kilometers. A planet reshaped by cataclysmic eruptions and alien geology. Aside from a few haunting, grainy photos from the surface, Venus kept its secrets hidden for centuries. No one had truly seen what lay beneath the veil until Magellan. On the 4th of May 1989, Space Shuttle Atlantis launched its third flight from the Kennedy Space Center. On board, it carried a very special payload, the first deep space probe launched by a space shuttle, a probe bound for Venus that was about to make history. For 4 years, the Magellan spacecraft ambitiously studied our nearest neighbor, mapping 98% of its surface to a resolution of up to 100 meters. The images it sent back shattered our assumptions of Venus forever. And that's what I'm going to show you today. I'm Alex McColgan and you're watching Astrum. Join me today as we explore the stunning images of Venus NASA's Magellan mission sent back, the surprises they revealed about Venus's violent past, and the mysteries that still linger unanswered to this day. Mariner 10 snapped some of the first pictures of Venus in 1974, capturing Venus's dense cloud formations on its way to Mercury. A year later, the Soviet Union's Venera program landed a spacecraft on the rocky planet, sending back the first and only images from Venus's surface. They show a desolate, eerie landscape, but these images only captured data from tiny portions of the planet's surface. The lander's cameras could only see a few meters in any direction and were destroyed within hours by Venus's crushing pressures. In the 1970s, the Pioneer Venus orbiter, also known as Pioneer Venus 1 or Pioneer 12, provided some radar mapping data, but its resolution was low and its images incomplete. Imagine trying to map the Earth, but Google Maps didn't let you zoom in further than 75 kilometers. New York City would just be 1 pixel, so pretty hard to make an accurate map. Additionally, Pioneer 12 didn't map the northern and southernmost parts of Venus. That's like a map of Earth with most of the Arctic and Antarctic circles missing. NASA decided they could do better. They wanted to see it all: landforms, tectonics, impact and chemical processes, erosion, and even get to know Venus's interior. So they mounted an ambitious mission to capture the entire surface of the planet in ultra-high detail, along with a gravitational map that would give insights into what lies beneath. That mission was Magellan. Now, before I show you Magellan's photos, you need to understand 3 key engineering innovations that made Magellan's mission so groundbreaking. First, to penetrate Venus's dense atmosphere, Magellan improved on Pioneer's basic radar altimetry. Engineers used a 3.7 meter high-gain Voyager antenna and components from other past missions to create a synthetic aperture radar that collected multiple readings of each area from different orbital positions. These combined readings simulated observations from a much larger antenna, revealing unprecedented surface details. Second, Magellan followed a polar orbital path, scanning Venus in north-south strips during each of its 3-hour, 15-minute orbits. In total, it completed 6 243-day mapping cycles. Cycles 1 to 3 mapped the planet's surface, and cycles 4 to 6 captured gravitational field data. By the end of its first cycle on the 15th of May 1991, Magellan exceeded its 70% mapping goal, covering 83.7%. By the end of cycle 3, it had mapped 98% of Venus at 100 to 250 meter resolution. The probe ended up sending home more data than all of NASA's previous planetary missions combined, a total of 150 gigabytes. By today's standard, it admittedly isn't that impressive. Your phone probably has more storage capacity. But for the early 90s, it was quite something. Finally, after its third mapping cycle in September 1992, Magellan transmitted a continuous radio signal to NASA's Deep Space Network. Based on how the probe's acceleration changed as it orbited the planet, this would produce a change to the radio signal via the Doppler effect, allowing scientists to decipher Venus's gravity field. This revealed information about the planet's interior structure and density distribution. The images I'm about to show you are 10 times sharper than any previous radar images taken from Earth or orbiting spacecraft at the time, and 250 times sharper than Pioneer 12's data. For the first time, we actually got to see what was lurking under those thick, noxious clouds. Let's take a look. Where previous missions had only shown vague outlines, Magellan revealed a world in exquisite detail, revealing for the first time the surface characteristics of our next door neighbor. This mosaic took a decade to put together, with the bulk of the radar data coming from Magellan's readings. Let's zoom in even further and take a little tour. When you approach Venus, you immediately notice the lack of craters. Compared with the Moon or Mars, it's pretty untouched, with Magellan only identifying 940 impact craters across the entire planet. Many small impact craters are missing because their meteors burn up in Venus's atmosphere, and the other craters we did find didn't look as expected. Take these 3 craters for example: Howe, Danilova, and Aglaonis. On impact, debris from the surface is ejected and forms the pale yellow blanket-like formations around each crater. Crater ejecta leave behind distinctive marks and shapes that help scientists determine the angle and energy of impact and how long ago it happened, the composition of surface and subsurface materials, and much more. What's interesting about these crater ejecta is they all show sinuous flows in a flower-shaped pattern, not unlike lava flows. They are made of molten rock and remain this way for way longer than expected due to Venus's high surface temperatures. The Adivar crater is another great example of Venus's unique ejecta patterns. On airless worlds like the Moon, ejected material from the impact follows an arced, ballistic path. But on Venus, the ejected debris interacts with the planet's dense atmosphere, creating powerful winds that sweep the material outward in ground-hugging flows. This creates unusual streaks, like the horseshoe-shaped one we see here, which are only found on Venus. Finally, the 90-kilometer wide Adams crater has a 600-kilometer outflow tail, likely made of impact melt or magma, which can remain in its liquid form for much longer due to the high temperature and pressure on Venus. The scarcity of these craters suggests Venus's surface is actually quite young. Indeed, gravity data collected by Magellan supports the hypothesis that Venus underwent a global resurfacing event approximately 300 to 500 million years ago. So, what could have caused such a dramatic event? Volcanoes? Lots and lots of volcanoes. We knew Venus had volcanic features before Magellan, but we had no idea that a staggering 85% of the planet is covered in volcanic flows. Like these pancake domes, 65 kilometers wide with broad, flat tops less than 1 kilometer tall. They likely formed from highly viscous lava, which later cooled and withdrew, leading to the cracks and pits you can see in the image. Or these sprawling lava flows, stretching for hundreds of kilometers over the fractured plains beneath two large shield volcanoes, Sapus Mons and Mart Mons. By studying the varying shapes and patterns of these volcanic plains, scientists can identify different volcanic formation processes, from localized shield volcano eruptions to massive regional lava flooding events. Speaking of Mart Mons, let's take a closer look. Towering at a dizzying 8,000 meters tall, it's almost as large as Mount Everest. It's also a shield volcano, characterized by its broad, gently sloping sides. They are typically formed by fluid lava flows, like the Mauna Loa in Hawaii. If you think Mart Mons looks as awesome as I do, and you want to carry around a bit of Venus's fire to spice up your day, then you should check out the wallpapers we have made over on Patreon for your phone, desktop or tablet. Shield volcanoes are not the only kind of volcano you'll see on Venus. Small volcanic domes like these are also very common features on the planet's surface. Unlike shield volcanoes, volcanic domes are formed by small, bulbous masses of lava too thick to flow very far. As it slowly exits the vent, the lava piles up and cools on the sides. This cluster of volcanoes sits between rough lava flows in the east and smooth lava flows in the west, indicating two different types of lava overlapping, though the exact process remains unknown. The abundance of lava flows and volcanic features on Venus confirmed that volcanism played a dominant role in shaping Venus's surface, and gave rise to the theory that the planet might still be volcanically active to this day. In 2024, researchers who were revisiting Magellan's archival data found that two volcanoes actually erupted during the probe's watch in the early 1990s. This supported a historic finding from the previous year that Mart Mons had also erupted in 1991. So, what's going on beneath the surface? What is Venus's mantle like? A hint to those answers lies in the surface coronae, like this 500-kilometer wide Yavin corona. When hot, upwelling magma from the depths of a planet's mantle reaches the surface, or the lithosphere, it leaves its mark. On Earth, our tectonic plates shift over this magma hotspot, creating volcanic chains like Hawaii, or flood basalts. But Venus only has one single tectonic plate. so mantle plume activity pushes the surface upward before collapsing as the magma cools. The result? These coronae. Despite being hundreds of millions of years old, many coronae appear well preserved. There are around 500 of them, widely distributed across the planet in patterns inconsistent with plate boundaries, and their characteristics suggest a lithosphere that is too thick or strong to break into mobile plates like Earth's. All this evidence suggests a unique style of lithospheric deformation where the crust stays largely in place, but is pushed, pulled, and deformed by forces below. This stagnant lid planet model might also play a role in Venus's runaway greenhouse effect. On Earth, our tectonic plates carry out vital processes like burying oceanic carbon. When it rains, atmospheric carbon interacts with mountain rocks to create new minerals which slowly make their way to the oceans and eventually find themselves stored in seabed sediment. This sediment is then subducted when an oceanic plate sinks the seabed back into Earth's magma layer, a process that regulates Earth's temperatures and the concentration of carbon dioxide in our atmosphere. Since Venus's crust is stagnant and devoid of tectonic activity, this regulatory process can't take place. Instead, heat builds up beneath the surface and greenhouse gases are not effectively removed from the atmosphere. The hotter the interior becomes, the more unstable the system, until the whole lithosphere overturns in a global resurfacing event, and the cycle begins again. We aren't exactly sure when the last resurfacing event occurred on Venus, but NASA's technical report following Magellan suggests it happened about 300 million years ago. Another curious symptom of Venus's unique tectonics and mantle activity are the tesserae that we can see in the highland regions of the planet. They are distinct geological features characterized by highly deformed terrain with a tile-like appearance. They cover about 8% of Venus's surface and are primarily found in the highland regions. As some of the oldest visible surface features on Venus, they date back about 750 million years. The USSR's Venera 15 and 16 missions first identified these formations in the 80s, but Magellan brought them to life in spectacular detail, like this photo of Alpha Regio, one of the most prominent tesserae on Venus. Scientists still aren't sure exactly how tesserae form, but the two leading theories indicate they are likely made of volcanic rocks, or they are part of Venus's continental crust, deformed through compression or expansion. If so, they'd be gateways into Venus's geological past, and possibly even show us what the climate was like billions of years ago. Fascinatingly, Magellan actually managed to capture the first evidence of active tectonics occurring on another planet in the solar system, in Venus's Aphrodite Terra, a continental area roughly the size of Africa. The image on the left was taken in late November of 1990 during Magellan's first trip around Venus. The image on the right was taken 8 months later, as the spacecraft flew over the region for the second time. See the bright, flow-like area that appeared? It's likely the result of a landslide, which was possibly triggered by a Venus quake. On the 13th of October 1994, after completing one of the most successful deep space missions ever, the probe made its final descent into the atmosphere of the planet it had studied so devoutly over the last 4 years. As it plunged towards the surface, it continued to transmit data about Venus's upper atmosphere until it was consumed by the intense heat and pressure. Over 30 years later, Magellan is still our primary source of information on Venus, and as any good mission, it raised as many questions as it answered. Was there ever water on Venus? If there was, would Venus have been habitable? How has the planet evolved through time? is Venus still volcanically active today? Together, NASA's upcoming Veritas and Da Vinci missions will set out to answer them and many more. Set to launch in 2028 to 2030, they will revolutionize our understanding of Venus once again. Da Vinci Plus will study Venus's clouds during 2 gravity-assist flybys, and also send a descent probe deep into Venus's atmosphere to get a better understanding of its gases, chemistry, and water history. Even though it isn't expected to survive the landing, the probe will collect valuable data and images on its hour-long descent to the planet's scorched surface. Meanwhile, the Veritas spacecraft will be a Venus orbiter, similar to MAVEN currently orbiting Mars. Over the 3 Earth years it spends circling our neighbour, its job will be to search for evidence of ongoing volcanism and tectonic activity by measuring heat coming from the surface and analysing the composition of Venus's tesserae. These findings will help us understand just how different, or similar, Venus and Earth are. Could our neighbour really be a window into our future? Or is it more like our hot, evil twin? Mercury, the solar system's closest planet to the Sun. Everything I'll show you today will be an actual picture or video image of Mercury from the MESSENGER probe. We'll discuss Mercury's orbit and rotation, its physical characteristics, its surface conditions, and the magnetic field and magnetosphere of the planet. I'm Alex McColgan and you're watching Astrum. Stick with me on this video and you will learn almost everything you could want to know about this tiny yet fascinating planet. Now, when you think about the physical characteristics of Mercury, I'm sure you imagine it being the closest planet to the Sun, but also that it's this giant rock floating in space. You wouldn't be too far wrong with that, but it is much more interesting than what you may first think. For example, when I look at Mercury, I do think of our moon, but Mercury actually is visually more appealing than our moon. Look at it in its true colour. The first thing that I notice is that it actually does have a colour. It's not just different shades of grey. And what else? Well, did you know, for example, that Mercury consists of approximately 70% metallic and 30% silicate materials? So it's actually more metallic than rocky. Because of this, Mercury's density is the second highest in the solar system at 5.427 grams per centimeter cubed, only slightly less than the planet with the greatest density, that of Earth, at 5.515 grams per centimeter cubed. If Mercury happened to be the same size as Earth, that would mean it would pretty much have the same gravitational pull at its surface. But being the size that it is, its surface gravity is only 3.7 meters per second squared. If you were to compare its gravity to Earth, it would look something like this. This means the surface gravity of Mercury is only slightly less than what it is on Mars, and considering that Mars is a much bigger planet, that just says something about the density of Mercury. But before we leave the subject of Mercury's size, I want to show you one last comparison, that of Ganymede and Titan against Mercury. Now, Ganymede is the solar system's biggest moon, and also the biggest moon of Jupiter, while Titan is Saturn's biggest moon, and the second biggest moon in the solar system. These two giant moons are bigger than Mercury, as you can see here, but their masses are far less. If you look closely at Mercury's surface, you'll see its appearance is similar to that of our moon. It shows extensive mare-like plains and heavy cratering, indicating that it has been geologically inactive for billions of years. But it obviously was geologically active at one point, because one of the distinctive features of Mercury's surface is the presence of many narrow ridges extending up to several hundred kilometers in length. It's believed that these were formed as Mercury's core and mantle cooled and contracted over time when the crust had already solidified. And one of the most distinctive things you'll notice about Mercury is this huge crater on its surface called Caloris Basin, with a diameter of 1,550 kilometers. The impact that created Caloris Basin was so powerful, it caused lava eruptions and left a concentric ring over 2 kilometers tall surrounding the impact crater. At the antipode of Caloris Basin is a large region of unusually hilly terrain known as the Weird Terrain. If you compare this region to the rest of Mercury, you can see why it would have this name. So, what's it like on the surface of Mercury? Well, to start with, the surface temperature is hugely different all over. It can range from minus 173 degrees Celsius to over 400 degrees Celsius. It never rises above minus 93 degrees at the poles though, because there's no atmosphere retaining the heat. This means that there's quite a big difference between the equator and the poles, but this variation is also due to its orbit and rotation, which we will get back to later. The subsolar point reaches about 400 degrees, while on the dark side of the planet the temperatures are, on average, minus 163 degrees Celsius. Because Mercury is too small and hot for its gravity to retain any significant atmosphere over long periods of time, it's not able to retain any of the heat it gets from being so close to the Sun, which is why the dark side of the planet is so much colder than the side facing the Sun. Mercury, however, does have an exosphere, which is like an extremely thin atmospheric-like volume surrounding the planet. Molecules in an exosphere are gravitationally bound to a planet, but the density is so low that it can't behave like a gas because the molecules don't collide with each other. In this picture, you can see the MESSENGER probe's view of Mercury's exosphere. When solar wind hits the planet, it rips off certain atoms out of the exosphere, and what's left is this trail of atoms going into space. We call this the planet's tail, and every planet has this to a certain extent. Earth even does have an exosphere, but it starts at 600 kilometers above the surface. It's really the point where space and the atmosphere meet. Now, in the case of Mercury, this exosphere is not at all stable. Atoms are continuously lost and replenished from a variety of sources. NASA has been able to confirm that craters at the North Pole of Mercury contain water ice. Mercury also has something which Mars lacks, an actual magnetosphere, or a magnetic field all around the planet. It is only about 1.1% as strong as Earth's, but it's still strong enough to deflect a lot of the solar wind around the planet. Now we're going to get to one of the things I find the most interesting about Mercury, its orbit and its rotation. Mercury has the most eccentric orbit of all the planets, with a distance from the Sun ranging from 46 million kilometers to 70 million kilometers. Now, this is something a bit hard to imagine, but bear with me. Mercury takes about 88 Earth days to complete an orbit around the Sun. It also has a 3-2 spin-orbit resonance of the planet's rotation around its axis. This means it spins 3 times around its axis for every 2 times that it orbits around the Sun. So although it takes about 59 Earth days for Mercury to rotate on its axis once, which is what we call a sidereal day, this 3-2 orbital resonance means that if you were actually standing on Mercury, it would appear that one day, from sunrise to sunrise, or what is called a solar day, is 2 Mercurian years. Standing on Mercury, that would look something like this. You would see the Sun rise relatively fast, and then as it approaches midday, it slows down and even starts going backwards before continuing on again to sunset. As you can see, that took a whole year, which means a nighttime on Mercury also takes a year. The Sun starts going backwards in the sky because approximately 4 Earth days before perihelion, the speed in which Mercury travels along its orbit equals the speed in which it's rotating. At this point, the Sun's apparent motion stays stationary. At perihelion itself, Mercury's orbital speed exceeds its rotational speed. So to a person actually standing on Mercury, the Sun appears to move backwards. 4 days after perihelion, the Sun's normal motion resumes. You can see this even clearer from a top-down perspective of Mercury. Twice a day on one of its poles, the Sun seems to pause and then continue on again. Something else to notice about Mercury's orbit is that it's inclined by 7 degrees to the plane of Earth's orbit. As a result of this, we can only see Mercury transit in front of the Sun when it's directly between us on Earth and the Sun itself. And because its orbit is inclined by 7 degrees, this only happens about once every 7 Earth years. The last thing we'll discuss about the rotation of Mercury is that its axial tilt is almost zero, with the best measured value as low as 0.027 degrees. This is even smaller than that of Jupiter, which has been measured at 3.1 degrees. And finally, do you want to see Earth from Mercury? Well, here we are, just a couple of pixels across. This photo was taken from the Messenger probe several years ago, and barring the newborns, every single one of us was in this picture. A massive thank you to our astronauts on Patreon. This video had no sponsors, but it was still made possible thanks to the hundreds of members we have there. Link is in the description to join our growing community. Patreon is where Astrum truly takes shape. A place for people who love space, who want to see these videos keep improving and reaching more curious minds. Every new member keeps the channel focused on what really matters, making the complexity of space available to everyone. If you enjoy what we do, come join the Astrum community today.